So, here's something worth thinking about as you settle in tonight. Right now, while you are lying there, something is moving through you. Not light, not sound, not air. Something that has no confirmed identity, no name beyond a placeholder, and no detection in any laboratory anywhere on Earth. If it is the kind of particle most physicists have bet on, roughly 1 billion of them are passing through your body every second. Through the mattress, through the floor, through the entire planet, and out the other side, without noticing that any of it was there. That substance makes up most of the matter in the universe. Not some of it, most of it. And after 90 years of looking, nobody knows what it is. That's what tonight is about. If you drift off somewhere along the way, that's perfectly fine. None of this needs you awake for it. The ideas will still be here in the morning. So let's start where the story actually starts. It starts on a mountain in Southern California with a man that almost nobody liked. Fritz Zwicky was Swiss, born in Bulgaria, and he arrived at the California Institute of Technology in 1925. He was brilliant, and he was difficult. He called colleagues he disagreed with spherical bastards, on the grounds that they were bastards whichever way you looked at them. He worked at Mount Wilson Observatory, up above Pasadena, back when the air over Los Angeles was still clear enough to see through. And in 1933, he did something fairly simple. He looked at a cluster of galaxies called the Coma cluster. The Coma cluster sits about 320 million light-years away in the direction of the constellation Coma Berenices. And it contains something over 1,000 galaxies, all bound together, all orbiting a common center of mass. From Earth, it looks like a scattering of faint smudges. Through the telescopes on Mount Wilson, it looked like a swarm. Zwicky wanted to know how much the swarm weighed. There are 2 ways to answer that. The first way is to count the light. You measure how bright each galaxy is. You work out roughly how many stars that brightness implies. You multiply by the mass of an average star, and you add it all up. It is rough, but it is honest, and in 1933, it was the best anyone could do. The second way is to watch how the galaxies move. This is the more elegant method, and it goes back to a piece of 19th century mechanics called the virial theorem. The idea is straightforward. In any system held together by gravity, the speed of the objects inside it depends on the total mass pulling on them. A swarm of galaxies with a lot of mass will whip its members around fast. A swarm with less mass will let them drift slowly. Measure the speeds, and you have measured the mass. You do not need to see any of it. You only need to see the motion. Zwicky measured the speeds using redshifts, and the answer he got was not what he expected. The galaxies in the Coma cluster were moving far too fast, not by a little, not by 50%, by a factor of hundreds. His original estimate was off by around 400 times, though the number has been revised downward substantially since then, because Zwicky was working with a badly wrong value for the expansion rate of the universe and a rough idea of how much light a galaxy actually produces. The modern figure for that particular cluster is closer to a factor of 5 or 10, but the direction of the error did not change. It has never changed. At the speeds he measured, the Coma cluster should have flown apart. There was not remotely enough visible material to hold it together. The galaxies should have scattered into the dark hundreds of millions of years ago, and yet there they were, still clustered, still bound, still orbiting something. Zwicky wrote it up in a Swiss journal in German, and he gave the missing material a name. He called it Dunkle Materie, dark matter. And here's the thing about that name. It is wrong, and it has been causing confusion ever since. Dark is what you call something that absorbs light. Coal is dark. A shadow is dark. This substance does not absorb light. It does not block light. does not scatter light or bend it or dim it in any way at all. Light travels through it as though it were not there, which, from light's point of view, it very nearly is not. The honest word would be transparent, or invisible, or, most accurately of all, non-interacting. But Dunkel Materie is what he wrote in 1933, and the name stuck, and now we are all a bit stuck with it too. He was not quite the first, incidentally. A year earlier, in 1932, the Dutch astronomer Jan Oort had been in Leiden studying the motions of stars in our own galactic neighborhood, measuring how quickly they bob up and down through the plane of the Milky Way. He also found more gravity than he could account for with visible stars. His result turned out to be mostly a measurement problem, and it does not hold up today. But the instinct was the same, and it arrived first. Nobody did very much about any of it. You might reasonably ask why. A result like that seems like it should have stopped everything. Somebody weighs a cluster of galaxies, finds that 90% of the mass is missing, and the field just carries on. Yes. Essentially, yes. For about 40 years. Part of the reason is that Zwicky was, professionally speaking, exhausting to deal with, and his more outlandish claims made people discount his sensible ones. Part of it is that the numbers involved were genuinely shaky, and everyone knew it. Estimating how much mass a galaxy has from how bright it looks is a chain of assumptions, and in the 1930s, every link in that chain was loose. It was much easier to assume that the light-to-mass conversion was simply wrong somewhere, or that clusters were not stable in the first place, than to assume that most of the universe was made of something nobody had ever seen. And honestly, that is a reasonable reaction. When your measurement says the universe is mostly invisible, the first suspect should always be the measurement. The suspicion just needed to survive being checked. Over and over. On different objects, at different scales, with different instruments, by people who did not know each other and did not particularly want the same answer. That took another 4 decades, and when it finally came, it came from a much quieter person, working on a much smaller object, with a telescope that was not even especially large. Let's go there next. Vera Rubin was born in Philadelphia in 1928, and she built her first telescope out of a cardboard tube when she was 14. She applied to Princeton for graduate school and was not sent an application form because Princeton did not admit women to its astronomy program and would not do so until 1975. She went to Cornell instead, and then to Georgetown, and she spent the early part of her career deliberately choosing problems that nobody else was fighting over, because the fights were unpleasant and the quiet corners were more interesting anyway. By the 1960s, she was at the Carnegie Institution in Washington, working with an instrument builder named Kent Ford. Ford had made something rather good, and it was an image tube spectrograph, and the important thing about it was sensitivity. A spectrograph takes the light from an object and spreads it out into its component colors so you can read the fingerprints of the elements inside it, and more usefully, so you can read how fast the object is moving toward you or away from you. That last part is the Doppler shift. Light from something moving away gets stretched toward the red. Light from something approaching gets squeezed toward the blue. The size of the shift tells you the speed. Older spectrographs needed a lot of light to work, which meant long exposures, which meant nights and nights on a cold mountain for a single measurement. Ford's tube amplified the incoming photons electronically before they hit the plate. It turned a week of observing into an evening. So Rubin and Ford pointed it at the Andromeda galaxy. Andromeda is the nearest large spiral galaxy to our own, about 2.5 million light-years away, and on a properly dark night, you can see it with your eyes as a faint oval smear in the autumn sky. And it is a disk of 1 trillion stars seen at an angle. And it is close enough that you can measure different parts of it separately. That is the whole trick. You can measure the center, and then move outward, and measure the middle, and then the far edge, and ask how fast each part of the disk is going round. Somebody had already tried this, and it is worth saying his name, because he tends to get left out. In 1939, a graduate student at Berkeley called Horace Babcock measured the rotation of Andromeda for his doctoral thesis. He found that the outer parts were moving surprisingly fast. He wrote it down. He suggested it might mean there was a lot of unseen mass out there, or possibly that light behaved strangely at those distances. His data were noisy, his instrument was limited, and almost nobody followed it up. He was 37 years early. Rubin and Ford published their Andromeda result in 1970, and this time the data were clean. Now, to understand why the result mattered, you need to know what everyone expected the answer to look like, and for that, it helps to think about the solar system. Mercury goes round the sun at about 47 kilometers per second. Earth does it at 30. Jupiter, much further out, manages 13. Neptune, right out at the edge, crawls along at 5.5. The pattern is clear, and it has been understood since Kepler and Newton. The further you are from the mass at the center, the weaker the pull, and the slower you have to travel to stay in a stable orbit. Speeds fall off with distance. They fall off in a very specific way, proportional to 1 over the square root of the radius. And that relationship is one of the most thoroughly confirmed things in all of physics. A spiral galaxy looks, from a distance, like a solar system. There is a bright, dense bulge in the middle where most of the visible stars are packed together, and then a thinning disk spiraling outward into darkness. So the expectation was obvious. Stars near the center should orbit quickly. Stars near the outer edge, far from the bulk of the light, should orbit slowly. Plot speed against distance, and you should get a curve that rises, peaks, and then falls away. That is not what Andromeda does. What Andromeda does is rise, and then flatten, and then just keep going. Stars at the outer edge of the disk, tens of thousands of light years from the center, well past where the visible material thins out to almost nothing, were moving just as fast as stars much closer in. The curve did not fall, and it went out flat, like a tabletop, as far as there was anything left to measure. Rubin and Ford did it again with another galaxy. Flat, and another. Flat. Through the 1970s, they worked through a sample of spiral galaxies, more than 20 of them by 1980, of every size and brightness and orientation they could reach. Nearly all of them were flat. It was not a quirk of Andromeda. It was what galaxies do. So what do you do with a result like that? Is the mass missing, or is the law wrong? Those were the only two options in 1970, and they are still the only two options now. Either there is material out there that nobody can see, or gravity does not behave the way Newton said at those enormous distances and those very gentle accelerations. And both of those ideas have been taken seriously by serious people ever since, and in parallel, working entirely separately, radio astronomers were finding the same thing and pushing it further out. Morton Roberts at the National Radio Astronomy Observatory in Greenbank, and later Albert Bosma in the Netherlands, were observing galaxies at a wavelength of 21 centimeters, which is the wavelength that neutral hydrogen gas emits. Hydrogen gas extends much further out from a galaxy than its stars do, sometimes 2 or 3 times further. It is a faint, tenuous halo of gas out beyond the visible edge, invisible to an optical telescope, and perfectly bright to a radio dish. Bosma's 1978 thesis mapped rotation curves out into that gas, well past the point where the starlight had faded to nothing. Still flat. So now you have optical astronomers and radio astronomers using completely different instruments and completely different physics, measuring the same thing and getting the same impossible answer. And that is the point at which a result stops being a curiosity and becomes a problem. And it is worth pausing here before we go further out, because this is the single most important observation in the entire story, and it is easy to let it slide past. Think about what a flat rotation curve actually says. Out at the edge of a galaxy, where there is almost no visible material, stars and gas clouds are moving at 200 kilometers a second or more. To hold something at that speed in a circular orbit, you need gravity. A lot of gravity. And gravity comes from mass. If the visible mass runs out, but the orbital speed does not drop, then there must be mass out there that you cannot see. And there must be a great deal of it. And it must be arranged in a very particular way. Specifically, the amount of mass enclosed inside your orbit has to keep growing as you move outward, steadily, almost linearly, long after the starlight has stopped. Rubin herself was careful about how she said this. She would point out that the observation was simply that galaxies rotate the wrong way, and that the missing mass was one explanation among several. She never oversold it. She also never got a Nobel Prize, despite being nominated repeatedly, and she died in December 2016 at the age of 88, at which point she had been the most obvious unrewarded candidate in astronomy for about 30 years. The prize is not awarded posthumously. That is simply the end of that story. So let's stay with the shape of the thing for a moment, because the shape is where the second confusion lives. If you assemble all the evidence about how the invisible mass around a galaxy is distributed, you do not get a bigger disk. You get a sphere. A vast, roughly spherical cloud that the flat, visible galaxy sits inside, like a coin dropped into the middle of a beach ball. Astronomers call it the halo. For the Milky Way, the visible disk is about 100,000 light-years across and a couple of thousand light-years thick. The dark halo around it is something like 600,000 light-years across, and it contains perhaps 10 times the mass of everything you can see. The disk you can photograph is a small, bright detail inside a much larger invisible object, which raises a fair question. Why a sphere? Everything else in the universe seems to flatten out. Solar systems are flat. Saturn's rings are flat. Spiral galaxies are flat. Even the accretion disks around black holes are flat. Flattening is what gravity does to a rotating cloud of stuff. So why does the dark matter refuse to do it? The answer is genuinely lovely, and it tells you more about what dark matter is than almost anything else we know. Things flatten because they can lose energy. Take a giant cloud of hydrogen gas drifting in space, slowly turning. Gravity starts pulling it inward. As it contracts, it spins faster, the way a skater pulls their arms in, and crucially, the gas particles bump into each other. Constantly, trillions of collisions, and every collision jostles an atom, and jostled atoms emit light, and that light escapes into space, carrying energy away with it. That is the key. The cloud is leaking energy. It cannot maintain its original height, and it sinks toward the plane it is rotating in, because rotation supports it sideways, but nothing supports it up and down. Over millions of years, the puffy sphere settles into a thin, spinning plate. That is why solar systems and galaxies are flat. Collisions plus radiation equals collapse. Dark matter cannot do any of that. It does not collide with itself, as far as anyone can tell. It does not collide with ordinary matter either, except through gravity, which is not really a collision at all. And it cannot emit light, because emitting light requires an electric charge to wiggle, and dark matter has no electric charge. It has no way to shed energy. None. So it just keeps moving. Each particle falls inward, swings through the center on some long looping orbit, and sails right back out to where it started, having lost nothing. Multiply that by an unimaginable number of particles on randomly oriented orbits, and you get exactly what we observe. A puffy, roughly spherical, permanently unsettled cloud. It cannot flatten because it has no way to cool down. And that single property explains an enormous amount. It explains why dark matter is spread thinly through the halo rather than concentrated in lumps. And it explains why there are no dark stars, no dark planets, no dark chemistry. Making a star requires gas that can collapse, and collapse requires cooling, and cooling requires interaction. Dark matter is stuck in a permanent diffuse fog. It has been that way for 13.8 billion years, and it will stay that way indefinitely. There is a version of this fact that people sometimes find unsettling, so it is worth saying plainly. There is dark matter passing through the room you are in right now. Quite a lot of it. It is not concentrated in space and thin near Earth. Earth is inside the halo, roughly 26,000 light-years out from the galactic center, moving through the dark matter fog at something like 230 kilometers per second. You are flying through it. It is flying through you. Nothing happens. That last part is the whole difficulty, and it is what the next 50 years of the story are about. But before we get to people building tanks of liquid xenon underground, there is a much bigger question sitting in front of us, and it is the one Zwicky would have asked. Rotation curves tell you about galaxies. Individual spiral galaxies, seen at an angle, whose gas you can trace. That is one kind of object in one situation. Is there a way to weigh something in the universe without relying on how it spins at all? Something that works on clusters, on odd shapes, on collisions, on things too far away to resolve? There is, and Einstein worked out the principle behind it, and then said in print that it would never be useful. The principle is that gravity bends light. In Newton's picture, gravity is a force that pulls on things with mass, and light has no mass, so light should sail straight past a star without caring. In Einstein's picture, published as General Relativity in 1915, gravity is not a force at all. It is the shape of space and time. A massive object curves the space around it, and everything traveling through that space follows the curve, including light, which has no choice in the matter. Light always travels in a straight line. It is just that the line itself is bent. This was confirmed in 1919 during a total solar eclipse by expeditions to Principe off the coast of West Africa and to Sobral in Brazil. Astronomers photographed the stars visible near the darkened sun and found them slightly displaced from where they should have been by about the amount Einstein had calculated. It made him famous overnight, and it is the reason his name means what it means. Then, in 1936, Einstein published a short paper working out what would happen if one star lined up exactly behind another. The foreground star's gravity would bend the background star's light around it on all sides, and you would see the distant star smeared into a perfect ring. He also wrote, in effect, that there was no hope of ever observing this, because the alignment required was absurdly precise and the effect was far too small. He seems to have thought the whole exercise was a bit of a waste of time, and published it mainly because someone had asked. A year later, in 1937, Zwicky pointed out that Einstein had been thinking too small. Do not use stars, Zwicky said. Use galaxies. Use entire clusters of galaxies. And they have vastly more mass, they cover much more sky, and the odds of a chance alignment are therefore far better. And here is the part that matters for our story. He noted that this would provide the most direct possible way of determining the mass of a cluster without any assumptions about starlight at all. He was right. It took 42 years for anyone to see it. In 1979, Dennis Walsh, Robert Carswell, and Ray Wayman were studying a pair of quasars that sat suspiciously close together in the sky, in the constellation Ursa Major. Quasars are the blazing cores of young galaxies, powered by supermassive black holes, and they are so far away and so rare that finding two side by side is odd. When the astronomers took their spectra, the two objects were identical. Not similar, identical. Same redshift, same emission lines, same everything. It was one quasar. There was a galaxy sitting in between, and its gravity was splitting the light into two paths around itself, so the same object arrived at Earth twice. They called it the twin quasar, and after that, the field opened up quickly. In 1986, astronomers looking at a galaxy cluster called Hubble 370 found long, thin, luminous arcs curving through it, which turned out to be the smeared images of much more distant galaxies behind it. Then came Einstein rings, actual complete circles, exactly as he had described and dismissed. Then came whole galaxy clusters acting as natural telescopes, magnifying objects behind them that would otherwise be far too faint to see. The Hubble Space Telescope, and now the James Webb Space Telescope, both use this constantly. Some of the earliest galaxies we know about were only findable because a cluster in the foreground happened to be magnifying them. And in every case, you can run the calculation backwards. The amount of bending tells you the amount of mass, and that is not an interpretation, it is just geometry. Measure how far an image is displaced, or how much an arc curves, or how strongly a background field is distorted, and general relativity hands you the mass of the object doing the bending. You never have to know anything about what that object is made of, or whether it glows, or how many stars it contains. So people did it, on cluster after cluster, and the masses came out 5 to 10 times larger than the visible material could account for. The same answer Zwicky got in 1933 with a completely different method. The same answer Rubin got in 1970 with a third, completely different method. There is a refined version of this called weak lensing, and it is now one of the main tools in cosmology. Most of the time, you do not get dramatic arcs. What you get is a subtle statistical squashing. Every galaxy behind a mass concentration gets very slightly stretched in a direction perpendicular to the line toward that mass. For any single galaxy, the effect is far too small to notice, because galaxies come in all shapes anyway, and you have no idea what shape that one started as. But if you measure 100,000 of them and average, the random shapes cancel out and the alignment survives. From that, you can draw a map, not a picture of light, a picture of mass. Survey telescopes have been building these maps across large patches of sky for 2 decades now, and the invisible material shows up as a vast web of ridges and filaments and knots, with the visible galaxies sitting inside the densest parts of it. Which brings us to the single most persuasive object in the whole subject, and probably the closest thing there is to a photograph of dark matter. It has a slightly ridiculous name. It is called the bullet cluster. About 3.8 billion light-years away, in the southern constellation of Carina, 2 enormous galaxy clusters ran into each other. The collision happened, from our point of view, roughly 150 million years ago, and we are seeing it from the side, at almost the perfect angle, which is an absurd piece of luck. One cluster punched through the other, and came out the far side, which is where the name comes from. Now, a galaxy cluster has 3 components, and they behave completely differently in a collision. The first component is the galaxies themselves. There are hundreds of them, but space is mostly empty, and galaxies are small compared to the distances between them. So when 2 clusters collide, the galaxies almost entirely miss each other, and they sail straight through, barely slowed, like 2 swarms of gnats passing. The second component is the hot gas, and this is the part people find surprising. Most of the ordinary matter in a galaxy cluster is not in the galaxies. It is in a thin, ferociously hot plasma filling the space between them at tens of millions of degrees, glowing in X-rays. In terms of ordinary mass, that gas outweighs all the stars and all the galaxies by something like a factor of 5 or 6. And gas does not pass through gas. When the 2 clouds met, they smashed, they compressed, they heated further, and they were left behind in the middle, dragging. The third component is whatever the dark matter is. So in 2006, a team led by Douglas Clow put 2 different images of this collision on top of each other. The first image came from the Chandra X-ray Observatory, which sees the hot gas. It shows 2 great glowing lobes of plasma sitting near the middle of the collision, one of them with a distinctive blunt bow shock giving the cluster its name. That is where the ordinary matter is, most of it. In the center, exactly where the physics says it should have piled up. The second image was a weak lensing map, built by measuring the distortions of hundreds of faint background galaxies. That shows where the mass is, and the mass is not where the gas is. The mass is in 2 separate clumps, well out on either side, sitting with the galaxies that passed through untouched. The bulk of the gravitating material had sailed straight through the collision without noticing it, exactly the way the galaxies did, and exactly the way something that does not interact with anything would be expected to. The ordinary matter is in the middle. The gravity is out at the edges. They have physically separated. That is what makes this object matter so much. Up to that point, someone could reasonably argue that all the missing mass evidence was really evidence that we have gravity slightly wrong. If gravity is a bit stronger than Newton says at very low accelerations, you could get flat rotation curves without any invisible material at all. We will come back to that idea properly, because it deserves a fair hearing, and it is not dead. But whatever version of it you write down, gravity in that picture is produced by the visible stuff. So the gravity has to be centered on the visible stuff. In the bullet cluster, it is not. It is 150,000 parsecs away from it in 2 separate lumps. Could those 2 lensing clumps simply be the galaxies themselves? No. The galaxies are there, and they are visible, and they carry only a small fraction of the total mass. Nowhere near enough to bend light that strongly. And could the gas have been pushed off to one side by something other than a collision? Also no. Gas glows in X-rays, and the X-rays show precisely where it is and how hard it was hit. There are now a dozen or so similar systems known, with names like Max J 0025, the Musketball Cluster, and Abel 520. Most of them show the same separation. Abel 520 is a genuine oddity that does not fit neatly and is still argued about, which is worth mentioning, because a field that only ever reports the tidy cases is not being straight with you. But the overall pattern is consistent, and it is hard to argue with a picture. So let's take stock, because by this point in the story, we know a fair amount. We know there is more gravitating mass in the universe than there is visible material. by a factor of roughly 5 or 6. We know it from the motions of galaxies in clusters, from the rotation of individual spiral galaxies, from the bending of light around massive objects, and from collisions where the mass and the light physically come apart. 4 independent lines of evidence using different instruments and different physics, agreeing on the same number. What we do not know is what it is, and the obvious first guess, the sensible boring guess, is that it is ordinary matter that simply is not lit up. This deserves real attention, because it is what any reasonable person would assume. The universe is full of things that do not glow. Planets do not glow. Cold gas does not glow much. Dust does not glow. Dead stars, burnt-out white dwarfs, neutron stars, black holes. None of these are visible in an ordinary photograph. Space is enormous and telescopes are limited. Why on earth would we jump to a new form of matter when the universe is plainly full of dark, ordinary things? That question has an answer, and the answer took about 30 years to assemble, and it is one of the more satisfying pieces of detective work in 20th century science. The suspects were given the name MACHOs, which stands for Massive Astrophysical Compact Halo Objects. And it was a deliberate joke, because the leading alternative candidate was called a WIMP, and physicists find this sort of thing funnier than everyone else does. A MACHO is any lump of ordinary matter big enough to be dark and small enough to be hard to spot. Brown dwarfs, which are failed stars too small to ignite. Rogue planets drifting between the stars. Cold white dwarfs. Neutron stars. Black holes of stellar mass. To test for them, astronomers used lensing again, in yet another form. If the halo of our galaxy were full of dark, compact objects, then every so often one of them would drift directly between us and a distant star. Its gravity would act as a lens and briefly focus that star's light toward us, and the star would appear to brighten and then fade back down over days or weeks in a smooth, symmetric curve with a very distinctive shape. The shape is the giveaway. Variable stars brighten and fade all the time, but they do it with the wrong profile and usually with a color change. A lensing event is achromatic. All colors brighten by exactly the same amount, because gravity does not care about wavelength. So through the 1990s, 2 collaborations, one called MACHO and one called EROS, monitored millions of stars in the Large Magellanic Cloud, night after night, for years, watching for those brightenings. They found some, just nowhere near enough. The final results, published in the mid-2000s, ruled out compact objects as the main component of the halo across a very wide range of masses. Somewhere in the region of a few percent could be hiding there, not 85%. The galaxy is not full of dark planets and dead stars. They exist. They are out there. They are simply nowhere near numerous enough. And then there is a much older and much harder constraint, which closes the door on ordinary matter completely, and it comes from the first 3 minutes after the Big Bang. When the universe was a few minutes old, it was hot enough and dense enough to be a fusion reactor. Not in one place, everywhere at once. Before that, it was too hot for anything to stick together. Protons and neutrons flying around at enormous energies simply cannot form nuclei, because any nucleus that briefly forms gets blown apart in the next instant. But the universe was expanding and therefore cooling. And after about a minute, it dropped below the threshold where nuclei survive. For the next couple of minutes, fusion ran. Then it stopped, because the density had dropped too low to keep going. The window was open for roughly 3 minutes, and then it closed for good. In that window, protons and neutrons combined into deuterium, which is hydrogen with an extra neutron, and then into helium, and a trace of lithium. and how much of each you end up with depends, very sensitively, on exactly one thing: how densely packed the ordinary matter was. Deuterium is the star of this, and it is fragile. It is easily destroyed by further reactions, and the amount that survives depends steeply on the density. Pack the protons and neutrons in tightly, and reactions run fast, and nearly all the deuterium gets processed into helium, leaving almost none. Spread them thinner, and the reactions stall, and more deuterium is left stranded when the window shuts. So if you can measure how much deuterium there is in the universe, you can read backwards to the density of ordinary matter in the first few minutes. It is a very direct measurement, almost embarrassingly direct. Measuring it is fiddly, but doable. You look at the light from distant quasars as it passes through ancient clouds of gas that have never been inside a star, because stars destroy deuterium, and you read the absorption lines. Astronomers have done this on a good number of such clouds now, and the answer is stable. Ordinary matter makes up about 5% of the total energy content of the universe. That is it. That is the whole budget for protons and neutrons and everything built out of them. Every star, every planet, every cloud of gas, every dead white dwarf, every one of us. 5%. So is there room to hide anything in that number? Could we simply have miscounted? A little, and it has happened. Astronomers spent years chasing what they called the missing baryons, ordinary matter that the census could not locate, and most of it eventually turned up in thin hot gas drifting between galaxies. That was a real discovery, and it still adds up to 5%, because 5% was always the total to be accounted for, and this constraint does not care whether the ordinary matter glows. That is the crucial part. It counts protons and neutrons, full stop. It does not matter if they are later assembled into brown dwarfs or rogue planets or interstellar dust or anything else you might hope to hide them in. The nuclear physics does not care what happens afterward. If the missing mass were made of protons and neutrons, deuterium would be far scarcer than it is. So the dark matter is not ordinary matter that failed to light up. It cannot be. It is not made of the same ingredients as anything you have ever touched. There is one exception people always ask about, and it is a good question. What about black holes made in the very early universe, before nucleosynthesis happened at all? Those would not be made of protons and neutrons in the relevant sense, because they would have collapsed before the counting started. Primordial black holes are a serious idea, and they have never quite gone away. Stephen Hawking wrote about them in the 1970s, and they had a real resurgence after 2015, when LIGO started detecting merging black holes with masses of around 30 times the Sun, which was heavier than anyone had expected, and made some wonder whether these were primordial rather than stellar. The constraints on them are severe, though, and they come from every direction. Very small ones would have evaporated by now through Hawking radiation, and we would see the gamma rays. Ones in the range of a planet's mass are excluded by the same microlensing surveys that killed the MACOs. Ones much heavier than a star would disrupt star clusters and wide binary star systems, which we can check and which are not disrupted. Ones in the stellar range would have altered the microwave background by heating the gas around them as they accreted. There are a couple of narrow windows left where primordial black holes could still make up all the dark matter, mostly around asteroid masses. It is not zero. It is just very cramped, and every year of new data makes it more so. So we are running out of familiar things. It is not dust. It is not gas. It is not planets or dead stars. And it is not black holes, probably. It is not antimatter, which people also ask about, because antimatter annihilates on contact with matter and produces a very specific flash of gamma rays that we do not see anywhere near enough of. The evidence keeps pointing at something genuinely new. Some particle or family of particles that is not in the standard model of physics and has never been made in any laboratory. And around the same time, this conclusion was becoming unavoidable. A completely different measurement arrived that pinned the numbers down with a precision nobody had expected, and did it using a signal that two engineers in New Jersey had originally tried to get rid of. The signal was noise. In 1964, Arno Penzias and Robert Wilson were working at Bell Labs in Holmdel, New Jersey, with a large horn-shaped antenna that had been built for satellite communications. They wanted to use it for radio astronomy, which meant they needed to understand every source of noise in the system. There was a hiss they could not remove. And it was faint, it was steady, and it came from every direction in the sky equally. It did not change with the time of day or the season or where they pointed. They checked the electronics. They checked the wiring. They found that a pair of pigeons had nested in the horn and coated the inside with what Penzias later described, with great delicacy, as white dielectric material, and they evicted the pigeons and cleaned the antenna. The hiss remained. About 60 kilometers away at Princeton, a group led by Robert Dick, including Jim Peebles, Peter Roll, and David Wilkinson, was building a detector to look for exactly this. The reasoning had been worked out years earlier by George Gamow, Ralph Alpher, and Robert Herman. If the universe began hot and dense, it was once an opaque, glowing fog. As it expanded and cooled, it eventually became transparent, and the light released at that moment should still be traveling now, stretched by the expansion into microwaves, filling all of space at a temperature just a few degrees above absolute zero. Penzias made a phone call. Dickey put down the receiver and told his group that they had been scooped. Two papers appeared together in 1965, one announcing the measurement and one explaining what it meant. Penzias and Wilson received the Nobel Prize in 1978. Peebles received one in 2019 for the theory that grew out of it. What they had found is called the cosmic microwave background, and it is the oldest thing anyone will ever see. It is a snapshot of the universe at about 380,000 years old, at the exact moment it turned transparent. Everything before that is hidden behind a wall of fog. Everything after that is history. Here is why it matters for our story. That snapshot is not perfectly smooth, and it is almost perfectly smooth, which is itself remarkable. But there are tiny variations in temperature from place to place, at the level of about 1 part in 100,000. Some patches are a fraction of a degree warmer, some a fraction cooler. Those patches are sound. In the hot, early universe, ordinary matter and light were locked together into a single fluid. Photons bouncing endlessly off free electrons, electrons dragging protons along with them, the whole thing behaving as one substance. And like any fluid, it could carry pressure waves, sound waves. Gravity pulled matter toward the denser regions, radiation pressure pushed back out, and the result was an oscillation. Compression, rarefaction, compression over and over, ringing through the entire universe for 380,000 years. Then the fog cleared, the photons flew free, and the ringing stopped instantly. What we see now is that sound frozen at the moment it was cut off, printed on the sky as a pattern of hot and cold spots, and you can measure that pattern very precisely. COBE, launched in 1989, detected the variations for the first time. WMAP, launched in 2001, mapped them properly. Planck, launched in 2009, mapped them to the limit of what is physically possible from that signal. What you get out is a graph called the power spectrum, which shows how much of the pattern appears at each angular size on the sky. It is not a flat line. It is a series of peaks and troughs, like the harmonics of a struck bell, and each one carries a different piece of information. The position of the first peak tells you the geometry of space. If the universe were curved, the hot and cold spots would appear at a different size than they actually are, the way a lens changes apparent size. The peak sits almost exactly where flat space predicts, which is how we know the universe is geometrically flat to within a fraction of a percent. The height of the first peak relative to the second tells you how much ordinary matter there is. Ordinary matter has mass, and mass makes the compressions deeper without making the rarefactions shallower, so it makes the odd-numbered peaks taller than the even ones. Measure the asymmetry, get the baryon density, and the answer that comes out is 5%. The same 5% that the deuterium gave, from completely different physics, at a completely different epoch, using a completely different measurement. Two independent methods, 400,000 years apart in cosmic time, agreeing to within a couple of percent. And that agreement is one of the quiet triumphs of the subject, and it almost never gets mentioned. The third peak is where dark matter shows up. Dark matter has mass, so it pulls, and it deepens the gravitational wells the fluid is falling into. But it does not feel radiation pressure, because it does not interact with light, so it does not push back out. It just sits there being heavy. That asymmetry, gravity without pressure, boosts the third peak in a way that ordinary matter cannot mimic. The third peak is clearly there in the data, and it is exactly as tall as a universe with roughly 5 times more dark matter than ordinary matter would make it. So now you have a fifth independent line of evidence from the early universe, from sound waves, from a signal recorded by a satellite in orbit, and it agrees with Zwicky and Rubin and the lensing maps and the bullet cluster. Planck's final numbers, published in 2018, are worth saying out loud because they are the summary of everything, and they are strange. Ordinary matter, everything made of protons and neutrons, everything on the periodic table, everything anyone has ever touched or measured or built anything out of, makes up about 5% of the energy content of the universe. Dark matter makes up about 27%, and the remaining 68% is something else entirely, which we have not talked about yet, and which is a separate mystery with a separate history. Those numbers shift by a fraction depending on which datasets you combine, and the last figure in particular has become interesting again very recently. But that is the shape of it. Everything familiar is a rounding error. Roughly 1/20th. Does that bother you? Should it? Everything that chemistry describes, everything biology is built out of, everything with a name and a symbol on the periodic table, is a minority component of a universe run by two things nobody has identified, and the universe has been arranged that way the whole time. We only found out about it very recently. So let's stay with dark matter a little longer, because there is one more thing the sky can tell us before we go looking for particles. And it is the thing that turns dark matter from a curiosity into the reason anything exists at all. Look at how galaxies are arranged in space. They are not scattered evenly, and they are not scattered randomly either. Surveys that map millions of galaxy positions in 3 dimensions, like the Sloan Digital Sky Survey, show a very particular structure. Galaxies sit along long, thin filaments, hundreds of millions of light years long. The filaments meet at knots, which are the great clusters. Between the filaments are voids, enormous, roughly spherical regions with almost nothing in them, some of them 300 million light years across. It is called the cosmic web, and it looks disconcertingly like the inside of a sponge or a neural network or the foam on the top of a wave. Zoom out far enough, and it does become uniform. On the largest scales, the universe is genuinely smooth, but on the scale of hundreds of millions of light years, it has this beautiful tangled architecture, and something had to build it. Here is the problem. Starting from the microwave background, you cannot build it in time. The variations in that early snapshot are tiny, 1 part in 100,000. Gravity does amplify small differences because a slightly denser region pulls a bit harder and gets denser still, and that is a runaway process. But the amplification is not fast. If you start with ordinary matter at 1 part in 100,000 and let gravity work on it for 13.8 billion years, you do not get galaxies. You do not get anything much. You get a slightly lumpy fog. There is a second problem too, which is worse. Before the fog cleared, ordinary matter could not clump at all. It was tied to the radiation, and radiation pressure smoothed out every lump as fast as gravity could make it. Ordinary matter was held flat for the entire first 380,000 years. It could not even start. Dark matter had no such restriction. It does not feel radiation pressure. So while ordinary matter was being held smooth, dark matter was already collapsing quietly in the background, building up a framework of dense regions, entirely invisible, entirely unimpeded. By the time the fog cleared and ordinary matter was finally released, the scaffolding was already there. The gas fell into wells that had been deepening for hundreds of thousands of years, and structure formed quickly because it had somewhere to fall into. You can test this properly, and this is where computers come in. You take a box representing a region of the universe. You fill it with a very large number of simulated particles. You set them up with exactly the tiny variations that Planck measured, and you let gravity run for 13.8 billion years of simulated time. The Millennium simulation did this in 2005 with about 10 billion particles. Illustrious TNG and its successors added the gas, the star formation, the exploding supernova, the black holes, all the messy ordinary physics on top. Run it with dark matter, and you get the cosmic web. Filaments, knots, voids, all of it, at the right sizes and in the right proportions. You can put a simulated map next to a real survey map and struggle to tell them apart. Run it without dark matter, and you get almost nothing. That is a strong test, and the simulations also pin down what kind of dark matter it has to be. Specifically, cold. Cold in this context does not mean low temperature in the everyday sense, and it means slow-moving relative to the speed of light back in the early universe when structure was forming. That turns out to matter enormously. If the dark matter particles were light and fast, which is called hot dark matter, they would stream freely out of small clumps before those clumps could collapse. Fast particles do not sit still in a shallow gravitational well. They cruise straight through and keep going, and they smear out any structure smaller than the distance they can travel. In that scenario, the biggest structures form first, and then fragment downward into galaxies. If the particles are heavy and slow, cold dark matter, they fall into even the smallest wells and stay there. Small structures form first, then merge upward into larger ones. The universe we observe formed from the bottom up. Small galaxies first, then bigger ones assembled from mergers, which is exactly what deep surveys show and exactly what the James Webb Space Telescope keeps confirming as it looks further back. So the dark matter is cold, which kills the most attractive candidate anybody had. Neutrinos were the obvious answer for a while, and it is easy to see why. They are real. They definitely exist. And they are produced in enormous quantities. They barely interact with anything, They are invisible, and there are something like 300 of them per cubic centimeter left over from the Big Bang everywhere in the universe. If you were designing a dark matter particle from scratch, you would basically design a neutrino. But neutrinos are extraordinarily light. The exact masses are still unknown, though we know the sum of the three is very small, well under a fraction of an electron volt. That makes them fast, hot. They stream out of small structures and prevent them forming, and a universe made of neutrinos looks nothing like the one we live in. So neutrinos are not it. They contribute a little, a fraction of a percent, and that is all. Which is genuinely frustrating, because it was the one candidate we knew for certain existed. Is there any way round that? Could there be a heavier kind of neutrino that nobody has found yet? Possibly. And that idea is still alive, and we will come back to it, because it has had a difficult decade. Now, I want to be honest about the trouble, because the cold, dark matter picture is not a clean sweep, and there is a set of persistent problems at small scales that people have been arguing about for 30 years. The first is called the core cusp problem. Simulations of pure dark matter predict that the density in the center of a galaxy's halo should rise steeply toward the middle, forming a sharp spike, a cusp. When astronomers measure the actual centers of small galaxies, particularly the faint dwarf galaxies where dark matter dominates completely, they often find a flat plateau instead, a core. The observed centers are gentler than predicted. The second is the missing satellites problem. Simulations predict that a galaxy like the Milky Way should be surrounded by hundreds of small dark matter clumps, each capable of hosting a dwarf galaxy. For a long time, we knew of about a dozen. The third has an excellent name. It is called too big to fail. The largest predicted satellite clumps around the Milky Way are so massive that they really should have formed visible stars, and yet the dwarf galaxies we actually observe are all less massive than that. The biggest predicted objects appear to be missing entirely. None of these is fatal, and all three have got better rather than worse over the last decade, which is the right direction. The missing satellites problem has largely dissolved. Deeper surveys have found dozens more Milky Way satellites, most of them ultra-faint objects containing only a few thousand stars, invisible to earlier instruments. The count has moved a long way toward the prediction, and it keeps climbing. The core cusp problem and the too big to fail problem both look increasingly like consequences of leaving out ordinary matter. Early simulations modeled gravity and nothing else, because that was all the computers could manage. Real galaxies have supernovae exploding in them, and the violent outflows of gas from those explosions drag on the dark matter gravitationally and can flatten a cusp into a core over time. Modern simulations that include this get much closer to what is observed. Still, there is a residual argument about the plane of satellites. The dwarf galaxies around both the Milky Way and Andromeda appear to lie in surprisingly thin, rotating planes rather than scattered randomly, and nobody has fully explained that. It might be a statistical fluke. It might not be. These are real open problems, and they are worth knowing about, because they are the seams in the theory, and the seams are where things eventually come apart or get sewn properly. They are also the reason that a rather different idea has refused to die for 40 years. In 1983, an Israeli physicist called Mordechai Milgrom at the Weizmann Institute published 3 papers proposing something that most of his colleagues considered close to heresy. His argument was straightforward. We have a discrepancy between the gravity we predict and the gravity we measure. And there are 2 ways to fix a mismatch like that. You can add matter that we cannot see, or you can adjust the law. Milgram noticed something specific about where the discrepancy shows up. It does not appear at a particular distance from the center of a galaxy. It does not appear beyond a particular size. It appears below a particular acceleration. The number is about 1.2 times 10 to the minus 10 meters per second squared. That is an almost incomprehensibly gentle tug. It is roughly the acceleration that would take you from a standstill to walking pace over the current age of the universe. Everywhere in the universe where gravity is stronger than that, Newton works perfectly. Everywhere gravity drops below it, things start moving faster than they should. So Milgram proposed that below that threshold, gravity does not weaken the way Newton says. Instead of falling off with the square of the distance, it falls off more gently, in direct proportion to the distance. He called it modified Newtonian dynamics, MOND, and with one adjustable constant, it produces flat rotation curves automatically, without any invisible matter at all. It should be said clearly that MOND is not the mainstream view, and it has serious problems, but it also has a success that genuinely bothers people, and pretending otherwise would be dishonest. The success is this: if you take a spiral galaxy and you measure only the visible material, the stars and the gas, MOND predicts the entire rotation curve. Not roughly, in detail, including the bumps and wiggles where a spiral arm adds a bit of extra mass, which show up as matching bumps and wiggles in the measured speeds. And it works for giant galaxies and for tiny ones, for gas-rich ones and gas-poor ones, across a range of about 5 orders of magnitude in mass. There is a very tight relationship called the baryonic Tully-Fisher relation, connecting a galaxy's total visible mass to the 4th power of its rotation speed, and MOND predicts it exactly. In the dark matter picture, it has to emerge from the messy details of how gas cools and settles inside halos, and getting it to come out that tight is hard work. For individual galaxies, MOND is uncomfortably good. Anyone who tells you otherwise has not looked at the plots. So why is it not the accepted answer? Why does almost nobody in cosmology work on it? Because a galaxy is not the only object in the universe, and MOND was built by looking at galaxies. And then it hits a wall, and the wall is everything larger than a galaxy. In galaxy clusters, MOND does not work. It reduces the discrepancy, but it does not remove it. You still need roughly twice as much mass as you can see. So a MOND advocate ends up needing dark matter anyway, which rather undermines the point of the exercise. The bullet cluster is worse. In a theory where gravity is generated by visible matter, the gravity must sit on the visible matter. In the bullet cluster, the two are demonstrably separated, and no version of modified gravity has produced a satisfying account of that. The microwave background is the hardest problem of all. Getting the third acoustic peak right requires something with mass that does not feel radiation pressure, and that is a property, not a bookkeeping adjustment, and modifying the force law does not give it to you. And there was one more blow. MOND, as Milgram wrote it, is not compatible with relativity, so in 2004, Jacob Bekenstein produced a relativistic version called TVES. Various versions of it predicted that gravitational waves and light would travel at slightly different speeds. In August 2017, LIGO and Virgo detected a neutron star collision, and telescopes caught the light from the same event about 1.7 seconds later, after a journey of 130 million years. The two speeds are identical to about 1 part in 10 to the 15. That result eliminated a great many modified gravity theories in a single afternoon. So where does that leave it? The honest position is that MOND is not a complete theory of the universe, and almost nobody working in cosmology thinks it will replace dark matter. but it is telling us something true that the standard picture does not explain well. There is an acceleration scale in galaxy dynamics, and it is really there in the data. Why should the behavior of dark matter halos know about a particular acceleration? Nobody has a good answer, and the people who work on this are entitled to keep asking. Science is allowed to have a theory that works brilliantly in one regime and fails in another. That situation is usually a sign that something is missing from both sides. Which brings us back to the search for the particle itself and to the strangest chapter in the whole story. For about 40 years now, people have been building machines to catch it. The machines have got 1,000,000 times more sensitive. Nothing has been caught. The favorite candidate for most of that time was the WIMP, the weakly interacting massive particle. And the reason it was the favorite is elegant enough to be worth explaining. In the very early universe, everything was in equilibrium. Particles were constantly being created out of energy and annihilating back into it. As the universe expanded and cooled, each species eventually fell out of that balance and froze out, leaving a fixed leftover amount that has been coasting ever since. How much is left over depends on how strongly the particle interacts. Interact strongly, and you annihilate efficiently, and almost nothing survives. Interact weakly, and a lot survives. Here is the part that made everyone excited. If you take a particle with a mass somewhere around 100 times the mass of a proton, interacting through the weak nuclear force at ordinary weak force strength, and you run that calculation, the amount left over today comes out at almost exactly the observed dark matter density. Nobody put that there. It falls out of the numbers. And it was called the WIMP miracle. And for a couple of decades it looked like the strongest hint anyone had. It got better, because theorists working on something completely unrelated had already predicted such a particle. Supersymmetry was invented to solve problems in particle physics that had nothing to do with astronomy. And its lightest stable particle, the neutralino, landed in exactly the right mass range with exactly the right interaction strength. Two entirely separate lines of reasoning pointing at the same object. That is normally how you know you are onto something. So people built detectors. The strategy is simple to describe and brutal to execute. If dark matter particles are streaming through the Earth, then occasionally one should strike an atomic nucleus and make it recoil, and if you have a large enough target and a quiet enough environment, you can see that recoil. The problem is that the environment is not quiet. Cosmic rays hit the surface constantly. Natural radioactivity is in everything, in the rock, in the concrete, in the steel, in the detector itself, in the dust. Against that, you are looking for a handful of events per year. So the detectors went underground, deep, under a mountain in Italy, at Gran Sasso, in an old gold mine in South Dakota, in a nickel mine in Ontario, under a mountain in Sichuan. A kilometer or more of rock filters out the cosmic rays. The detectors themselves are built from materials selected for extreme radio purity, lead smelted from Roman shipwrecks in some cases, because it has had 2,000 years to lose its radioactivity. The leading technology is a large tank of liquid xenon. A particle striking a xenon nucleus produces a tiny flash of light and a small cloud of electrons. And by reading both, you can reconstruct the energy and the position and work out whether it looks like a nucleus recoiling or an electron scattering. The names are LZ in South Dakota, Xenon T at Gran Sasso, Pandax in China. They have grown from kilograms to tons. How sensitive are they now? Sensitive enough to register a single xenon nucleus twitching somewhere inside 10 tons of liquid. Sensitive enough that one grain of dust with the wrong isotope in it can spoil a year of data. and still nothing arrives. And in 40 years, they have not seen dark matter. There is one exception, and it has been a running argument since the late 1990s. An experiment at Gran Sasso called DAMA and later DAMA Libra uses sodium iodide crystals rather than xenon, and it looks for something clever. The Earth orbits the Sun, while the Sun orbits the galactic center through the dark matter halo. In June, our orbital motion adds to the Sun's motion, so we plow through the dark matter slightly faster. In December, it subtracts. So the rate of dark matter collisions should rise and fall over the year, peaking around the start of June by a few percent. DAMA sees an annual modulation, and it has seen it for more than 20 years, with the peak in the right month, at very high statistical significance. Nobody else sees anything, and the parameters DAMA's signal would imply have been comprehensively excluded by the xenon experiments several times over. There are ways to wriggle out of that, involving dark matter that interacts with sodium and iodine very differently from how it interacts with xenon, but they are contrived. Experiments using the same sodium iodide crystals, called ANAIS in Spain and COSINE in South Korea, have been running specifically to check, and they do not reproduce it. So what is DAMA actually seeing? Nobody knows. The general view is that something seasonal about the laboratory or the equipment has not been identified, and the annual temperature cycle underground is a favorite suspect. The argument is not formally closed, and it has been going on longer than some of the people working on it have been alive. Meanwhile, the machines kept getting better, and the limits kept getting tighter, and the WIMP kept not appearing. The Large Hadron Collider was supposed to help. If supersymmetry existed at the energies people expected, the collider should have made those particles directly from about 2010 onward. It ran, and it found the Higgs boson in 2012, which was a triumph, and it found no supersymmetry at all. The simplest versions are now dead. The surviving versions require the particles to be much heavier than the original argument wanted, which weakens the whole motivation. Then, in December 2025, the LZ experiment in South Dakota published a result from 417 days of data taken between March 2023 and April 2025. It set the tightest limits yet on lower mass WIMPs, in the range of 3 to 9 times the proton mass. No dark matter. But it did see something else for the first time, and this is where the story gets a bit poignant. And it detected neutrinos from the core of the Sun at about 4.5 sigma significance. That is a genuine achievement, and it is also a warning. Solar neutrinos scatter off nuclei in almost exactly the way a light dark matter particle would. They are indistinguishable, event by event. Once your detector is sensitive enough to see them, they become a background you cannot remove, because you cannot shield against neutrinos, and you cannot turn off the Sun. This is called the neutrino fog. For low-mass dark matter searches, we have now entered it. For heavier particles, there is still clear air ahead, but the direction is obvious. There is a floor beneath this technique, and we are approaching it. The response has been to design something bigger, a next-generation detector called XLZD that merges the LZ, Xenon, and Darwin teams, and it will push further into the fog by sheer statistics. And attention has broadened enormously to other candidates, because the field has spent 40 years betting on one horse, and the horse has not appeared. The most popular alternative now is the axion. It was proposed in 1977 by Roberto Peche and Helen Quinn, and named by Frank Wilczek and Steven Weinberg, to solve a completely unrelated puzzle about why the strong nuclear force does not violate a symmetry that it is perfectly entitled to violate. The particle that falls out of that solution would be extraordinarily light, perhaps a millionth of the mass of an electron or far less, and produced in vast numbers in the early universe, and cold despite being light because of how it was made. Axions are hunted completely differently. You put a resonant cavity inside a very strong magnetic field and wait for an axion to convert into a photon of a specific frequency, then slowly tune the cavity across the possible frequency range, listening for a whisper. ADMX at the University of Washington has been doing this for years, along with a growing number of others. They have not found it either, but the searched region is still a small fraction of the possible range, so the silence means much less than it does for WIMPs. Beyond that, there are sterile neutrinos, which would be a heavier cousin of the neutrinos we know that does not feel the weak force at all. There was an exciting moment around 2014 when an unexplained X-ray line at about 3.5 kilo electron volts turned up in observations of galaxy clusters, which some suggested was sterile neutrinos decaying, and it has not held up well under closer inspection, and is now mostly regarded as an instrumental or atomic physics effect. And beyond that, there are whole families of ideas that get less press. Fuzzy dark matter made of ultralight particles with quantum wavelengths the size of a galaxy. Self-interacting dark matter that can bump into itself and would naturally produce the flat cores we observe in dwarf galaxies. Entire hidden sectors with their own forces and their own particles, coupled to us through gravity and almost nothing else. That last possibility is worth sitting with for a second, because it is the one that would be hardest to accept and is entirely allowed by everything we know. There may be no laboratory detection ever. If dark matter interacts through gravity alone, then no detector on Earth of any design will ever register it, and everything we ever learn about it will come from watching how it moves things on scales of thousands of light years. So that is the state of the search. 5 independent lines of evidence say the stuff is real and say how much of it there is. 40 years of increasingly exquisite experiments have not caught a single one, and the leading theoretical candidate has quietly lost most of its motivation. That is where dark matter stands. And in 1998, while all this was going on, 2 teams of astronomers doing something completely unrelated found a second thing wrong with the universe, and it was bigger. They were trying to measure how fast the expansion of the universe was slowing down. That was a perfectly sensible thing to want to know. The universe has been expanding since the beginning, and it is full of matter, and matter attracts. So the expansion should be decelerating. The only question was, by how much, and the answer would tell you the fate of everything. Enough matter, and the expansion would eventually stop and reverse, ending in a collapse. Too little, and it would coast outward forever, slowing, but never quite stopping. To measure that, you need to compare distant objects with nearby ones. Look at something far away, and you are looking back in time, so you can measure the expansion rate then and compare it to now. What you need is a standard candle, an object whose true brightness you know, so that its apparent brightness tells you its distance. The candle they used is a type of exploding star called a Type 1, a supernova. These happen in binary systems where one star is a white dwarf, the dense, burnt-out core left behind when a star like the Sun dies. A white dwarf sitting alone will simply cool for eternity. But if it has a companion, it can pull material off it, and if it accumulates enough mass, it crosses a threshold, and at that point, the whole object detonates in a runaway nuclear explosion that destroys it completely. The useful part is that the threshold is always the same, so the explosions are always roughly the same size. and they are bright enough to be seen across most of the observable universe, briefly outshining the entire galaxy they sit in. They are not perfectly identical, but there is a fix for that. In 1993, Mark Phillips showed that the ones that fade slowly are intrinsically brighter than the ones that fade quickly, in a tight and predictable way. So you watch the light curve, you measure the fading rate, you correct for it, and you get a true brightness good to a few percent. Two teams set out to do this. The High Z Supernova Search Team, led by Brian Schmidt with Adam Rees, doing much of the analysis, and the Supernova Cosmology Project at Berkeley, led by Saul Perlmutter. They were rivals, they were working independently, and they did not much like each other. Both teams got the same answer, and neither of them believed it. The distant supernovae were too faint. Not by much. About 25% fainter than they should have been, which sounds small, but is enormous when your measurements are good to a few percent. Too faint means further away than expected. Further away than expected means that the universe had grown more since that light left than a decelerating model allows. The expansion is not slowing down. It is speeding up. Rees has described going through the analysis repeatedly looking for the mistake and getting a number for the deceleration that kept coming out negative, which is a physically absurd result to write down. Perlmutter's group spent months on the same hunt. Both teams checked whether dust could dim the light. Dust reddens as well as dims, and the supernovae were not reddened. They checked whether ancient supernovae might be intrinsically different from modern ones, and they checked their calibrations against each other. The answer would not go away. Both teams published within months of each other in 1998 and early 1999, and they agreed. Something is pushing the universe apart, and it is getting more effective as time goes on, and it now dominates everything. Although pushing is the wrong word, and it is worth being careful with it, because this is where most of the confusion lives. Dark energy is not a force. Nothing is blowing outward from any particular place. What is happening is that space itself is being created between things, everywhere at once, and the rate at which it appears is climbing. Does that mean you are expanding too? No. Anything held together by an actual force stays held together. Chemistry holds you together. Gravity holds the Earth together, and the solar system, and the galaxy. None of those are growing. The expansion only reveals itself across the vast, empty gaps where nothing is holding anything to anything else. Michael Turner gave it a name later that year, dark energy, which has all the same problems as dark matter as a name, plus a new one, because it makes people think the two things are related. They are almost certainly not. They are separate mysteries that share an adjective. Schmidt, Rees, and Perlmutter received the Nobel Prize in 2011. So what is it? The leading candidate is an idea Einstein had in 1917 and then abandoned. When he first applied general relativity to the universe as a whole, he found that his equations would not permit a static universe. Everything wanted to either collapse or fly apart. And this was a problem, because in 1917, everybody knew the universe was static. So he added a term, a constant, that acted as a slight outward pressure built into space itself, tuned precisely to hold everything still. He called it the cosmological constant, and he wrote it with the Greek letter lambda. Then in 1929, Edwin Hubble showed that the universe is expanding, using earlier distance work by Henrietta Swan Leavitt and building on theoretical results from Georges Lemaitre and Alexander Friedman. The static universe was wrong. The constant was not needed. Einstein dropped it. There is a famous story that he called it his greatest blunder. That story comes to us through George Gamow, who was fond of a good line, and there is no record of Einstein saying it himself. It is probably best treated as something Einstein might have said rather than something he definitely did. The constant came back in 1998 because a constant outward pressure in space is exactly what the supernovae were showing. And it has a natural physical interpretation, which is where things get uncomfortable. In quantum field theory, empty space is not empty, and it has a lowest possible energy state, and that state is not zero. Pairs of particles flicker in and out of existence constantly, and the vacuum has an intrinsic energy density. That energy would gravitate. And because it is a property of space itself, rather than a substance sitting in space, making more space makes more of it, and its density stays constant as the universe expands. That last point explains the timing, and the timing is one of the things people find most confusing. Matter dilutes as the universe expands. Double the size and the density falls by a factor of 8. Dark energy does not dilute at all. So in the early universe, when everything was packed close, matter dominated and gravity won, and the expansion decelerated, exactly as everyone assumed. But the matter kept thinning out, and the dark energy did not. And about 5 billion years ago, the two crossed over. Since then, dark energy has been in charge, and the expansion has been accelerating. We happen to be living just after the crossover point. That is either a coincidence or a clue, and it has a name, the coincidence problem, and no accepted resolution. And what is the universe expanding into? Nothing. That question feels unavoidable, and it has no answer, because it assumes the universe sits inside some larger room with walls. As far as anyone can tell, it does not. There is no edge and no outside. There is only more space appearing between the things that are already here. So we have a natural candidate with a clear physical origin. And when you try to calculate how much vacuum energy quantum field theory actually predicts, you get the worst quantitative failure in the history of physics. The predicted value exceeds the observed value by somewhere between 50 and 120 orders of magnitude, depending on how you set up the calculation and where you cut it off. 120 orders of magnitude is a 1 followed by 120 zeros. There is no polite way to describe an error of that size. It is not that the calculation is difficult, and it is that the answer is so catastrophically wrong that something fundamental must be missing, and nobody knows what. Various proposals exist for why the enormous contributions might cancel almost exactly, leaving the tiny residue we observe, and none of them is convincing, and the cancellation has to be precise to 120 decimal places to work. That is the state of the leading theory. It fits every observation beautifully, and its predicted magnitude is wrong by more than any prediction has ever been wrong. The main alternative is called quintessence, which imagines dark energy as a dynamic field rather than a fixed constant, one that can change strength over time. The advantage is flexibility. The disadvantage is that it does not solve the underlying problem, it just moves it, and it introduces new parameters with no independent motivation. And that distinction, constant versus changing, was academic until quite recently. It has become the most interesting question in cosmology in the past 2 years. The instrument responsible sits on the Mayall 4-meter telescope at Kitt Peak in Arizona, and it is called DESI, the Dark Energy Spectroscopic Instrument. It has 5,000 tiny robotic positioners on its focal plane, each holding an optical fiber, and each one can be repositioned in about a minute to point at a different galaxy. And it takes 5,000 spectra at a time, all night, every clear night. The point of all that is to build the largest 3-dimensional map of the universe ever made, and to use it to measure a very specific ruler. Remember the sound waves in the early universe. When the fog cleared and the ringing stopped, it left a preferred scale frozen into the distribution of matter, a slight excess probability of finding two galaxies about 500 million light-years apart rather than any other separation. It is faint and statistical, and you need enormous numbers of galaxies to see it, but it is there. It was first detected in 2005 in the Sloan survey. It is a ruler of known length, sitting at every distance and therefore at every epoch. Measure how big it appears at different redshifts, and you trace the expansion history directly. DESI released its first year of data in April 2024 and its second in March 2025, and completed its planned survey in April 2026. Taken entirely on its own, the data are consistent with a plain cosmological constant. But when you combine them with the microwave background, with the supernova samples, and with weak lensing surveys, a preference emerges for a dark energy that has been getting weaker, not vastly weaker, but the numbers prefer a model where the outward push was stronger in the past and has been declining. Depending on which supernova compilation you use, the preference sits somewhere around 3 to 4 sigma. Physics conventionally requires 5 before calling something a discovery, and 3 to 4 sigma results have evaporated before. Several groups have argued that the effect is really a systematic problem in the supernova calibrations rather than cosmology. But it is the most interesting number in the subject right now, because if dark energy is not constant, then it is not vacuum energy, and the leading explanation is simply wrong, and it also changes the ending. A constant dark energy expands the universe forever at an accelerating rate. A weakening one might eventually let matter win again. And there is a second crack, which is older and more stubborn. There are two good ways to measure how fast the universe is expanding today, a number called the Hubble constant. The first is to build a distance ladder. Start with objects near enough to measure by parallax. Use those to calibrate Cepheid variable stars, whose pulsation period tells you their brightness. Use Cepheids to calibrate Type 1, a supernovae in nearby galaxies, and use supernovae to reach far out. Adam Rees has led this effort for years, and the answer comes out around 73 kilometers per second per megaparsec. The second is to take the microwave background, which contains the physics of the early universe in exquisite detail, feed in the standard model of cosmology, and calculate what the expansion rate must be today. Planck's answer is about 67.5. Those two numbers do not overlap, and the error bars on both have been shrinking for 20 years, which has made the gap worse rather than better. It now sits at roughly 5 sigma, which is the same standard that would count as a discovery in any other context. An enormous amount of effort has gone into finding a mistake. People have rebuilt the distance ladder using red giant stars instead of Cepheids, which gives an intermediate answer around 70. The James Webb Space Telescope has been used to resolve crowded Cepheid fields that were suspected of contamination, and the crowding does not appear to explain it. Gravitational lensing time delays and gravitational wave sirens provide independent routes, and their precision is improving. The tension has survived every attempt to kill it. It might still be a systematic error nobody has found, or it might be telling us that the standard model of cosmology is missing something between the microwave background and today, which is precisely the interval where dark energy operates. So let me put the whole thing in one place, honestly, because you have been generous with your time, and the summary should be straight. We know with high confidence that there is about 5 times more gravitating matter in the universe than there is visible matter, and we know it from 5 independent kinds of observation that have no reason to agree and do. We know that matter is not made of protons and neutrons because the deuterium and the microwave background both count those separately, and there are not enough. We know it is slow-moving and does not interact with light, because otherwise the cosmic web would not look the way it does. We do not know what it is. 40 years of direct searching have found nothing. The favorite candidate has lost most of its theoretical motivation, and we are now running into a floor of solar neutrinos that limits how much further this particular technique can go. We know with high confidence that the expansion of the universe is accelerating, from supernovae, from the microwave background, and from the sound wave ruler measured in galaxy surveys. We do not know why. The best explanation is a constant energy in empty space, which fits the data very well, and whose predicted magnitude is wrong by a factor with 120 zeros in it. Recent data hint that it might not be constant after all, at a significance that is interesting and not yet decisive. And there is a 5 sigma disagreement between 2 good measurements of the current expansion rate that nobody has been able to explain away. 95% of the universe is something we cannot name. Not cannot see. Cannot name. Is that embarrassing? A little. Is it a crisis? Not remotely. I want to be clear that this is not a failure. It is unfinished, which is different. In 1895, you could have written a similar list about the atom. Nobody knew what held it together. Nobody knew why hot objects glowed the colors they did. Nobody knew why the orbit of Mercury was slightly wrong. Those 3 loose ends turned into quantum mechanics and general relativity within 30 years. Dark matter and dark energy are that kind of problem. They are not gaps in a finished picture. They are the places where the next picture is going to come from. The instruments are already looking. The Vera Rubin Observatory in Chile, named for the woman who measured the rotation curves, began surveying the entire southern sky repeatedly and will find millions of supernovae. The Euclid Space Telescope is mapping the shapes of over 1 billion galaxies to trace how dark matter has clumped over 10 billion years. The Nancy Grace Roman Space Telescope will do something similar with a field of view 100 times larger than Hubble's. XLZD will go deeper into the neutrino fog. Axion searches are widening their range every year. One of those may find something, or the answer may come from somewhere nobody is currently looking, which is how it has usually happened before. So let's come back down. Start out at the largest scale, where the cosmic web hangs in the dark. Filaments of invisible material, hundreds of millions of light years long, with galaxies strung along them like water beating on a thread. Voids between them so empty that a galaxy sitting in the middle of one would have nothing bright anywhere in its sky. All of it slowly being pulled apart by whatever dark energy is, a little faster every billion years. Come inward to one knot in that web, a cluster of 1,000 galaxies wrapped in a cloud of gas at 50 million degrees, all of it held together by a halo of something nobody has identified. Zwicky's Coma cluster is still up there tonight, in the direction of Coma Berenices, doing exactly what it was doing when he pointed a telescope at it from Mount Wilson in 1933. Come inward again, to one galaxy on one filament, a spiral, 100,000 light years across, turning once every couple of 100 million years, and around it, 6 times larger and far more massive, an invisible sphere with no edge you could point to, the thing Vera Rubin measured without ever seeing it. Come inward again. 2/3 of the way out from the center of that spiral, on the inner edge of a minor arm, there is an ordinary yellow star. and it has been going round for about 4.5 billion years, at 230 kilometers per second, plowing through the dark matter as it goes. Come inward. The third planet. Mostly water, thin shell of air, the whole biosphere thinner in proportion than the skin on an apple. And come all the way in, to the room you are lying in right now. The weight of the blanket, the mattress underneath you, the particular quality of dark behind your eyes. Here is the thing about all of that scale. You are not separate from it. The calcium in your bones was made inside a star that exploded before the sun existed. The iron carrying oxygen around your body right now was forged in the final seconds of a stellar collapse. The hydrogen in every molecule of water in you was made in the first few minutes after the Big Bang, in that same 3-minute window that also set the deuterium abundance we use to prove that you cannot be made of dark matter. That hydrogen is 13.8 billion years old. It has been through clouds and stars and rain and rivers, and tonight, some of it is in you, and it is the oldest thing you will ever hold. And the dark matter is here too, passing through the room, passing through the bed, passing through you, at a couple of 100 kilometers a second, in numbers nobody can quite pin down, having last interacted with anything at all, somewhere back in the first fraction of a second of the universe. It has been doing that for your entire life, and it did it while you were asleep last night. It is doing it now. Nothing happens. That is the whole point. There is no sensation, no effect, no consequence at your scale whatsoever. It only shows itself across distances so vast that you have to measure them in the time light takes to cross them. You do not have to remember any of this. Not the names, not the numbers, not the order it happened in. Zwicky and Rubin and Penzias and Milgram and Perlmutter will still have done what they did, whether or not you can recall it in the morning. The Coma cluster does not need to be observed to keep holding together. None of it needs anything from you. That is quite a restful thought when you sit with it. 95% of the universe is unidentified, and it has been getting along perfectly well regardless. And it will carry on getting along perfectly well long after everyone currently working on the problem has stopped working on anything. Somebody will probably solve it. Perhaps in 20 years, perhaps in 200. The answer will turn out to be something that seems obvious afterwards, the way things always do. And it will not be more remarkable than the fact that a species on a small, wet planet worked out that most of the universe was missing by watching how fast some smudges of light were moving. So let that settle. The halo is out there in the dark, holding the galaxy together, the way it has for 13 billion years. The expansion is carrying on, very slightly faster this year than last, and the oldest light in the universe is still arriving, from every direction at once, falling on the roof above you at this moment, faint and cold and perfectly steady. It'll all still be out there in the morning. So just rest